So we are going to learn about the Henderson Hasselbalch equation. This is also referred to in some books as HH equation, and commonly students call it as buffer equation also. So let's just see what is the Henderson Hasselbalch equation. Consider the ionization of a weak acid, HA giving H positive and A minus. As we know, we can write the Ka of that. Ka is written there. Let's rearrange the Ka in terms of hydrogen ions. And after I write it in terms of hydrogen ions, I'm taking negative log on both sides. And I get negative log concentration of hydrogen ions equals negative log KaHA divided by A minus. So if I separate out the equation, I get negative log hydrogen ions, which I can call as pH, and I get negative log Ka, which I can call as pKa, minus log HA over A minus. So the same equation rearranged as pH equals pKa plus log of concentration of A minus divided by HA is called as the Henderson Hasselbalch equation. I know why is this Henderson Hasselbalch equation useful? So just for reference, the equation is given again. Just imagine if we have concentration of A minus equals concentration of HA, in that case pH is equal to pKa. Or in other words, if I need some pH, a solution of some pH, the only thing I have to look at is the pKa of the acid. And if I take an acid which is close to the pH, which has a pKa value close to the pH value, I will get the solution with the desired pH. Therefore, this is the one which helps us to pick up the acid conjugate base combination to attain the desired pH. So how do we do it? Consider the table on the side. I have given you the Ka value of some of the acids, and the pK is also given. For ammonia, it is the base is ammonia, and the ammonium ion is given there because I am going to take up only the pKa values. So suppose if I need a pH close to 4 or something between 3 to 4. In that case, the combination I will take will be HF and its conjugate base NaF, or the acid HNO2 and the conjugate base NaNO2. So if I want something close to 5, the best combination will be, look at the pKa value, it is the acetic acid sodium acetate buffer. And anything close to 7 or less than 7, I can use the carbonate bicarbonate buffer. And a pH from 9 to 10, I can use HCN NaCN or the ammonium hydroxide ammonium chloride combination. So if you want exactly some other pH, suppose if you want a pH of 8 or say a pH of 3 or a pH greater than 10, we can adjust the concentrations of A minus and HA in such a way that I get the desired pH. Now let's do a question based on a Henderson Hasselbalch equation. Buffer solution is made from 0.20 molar H2CO3 and 0.15 molar sodium bicarbonate. We have to calculate the pH of the solution, and also after calculating the pH, we need to find out the concentration of the acid to get a pH of 7.9. So let's do the first part of the question. Calculating the pH, apply the Henderson Hasselbalch equation. Ka is given, concentration of A minus is given, concentration of HA is given. Substitute all of them into the equation, and you can calculate the value of pH, and that's equal to 6.2. Now we have got the pH. Let's go to the second part of it. They are asking you to find the concentration of the acid to get a pH of 7.9. So same way, substitute all the values into the Henderson Hasselbalch equation. 7.9 is the pH I want, and Ka value is given there, and then log the concentration of the bicarbonate remains the same, so I use the same value 0.15 and divided by the concentration of the acid HA, which I am supposed to find. So when I calculate it, I get the concentration of acid as 0.005 molar. Calculate the pH of 1 liter of 0.10 molar HF and 0.20 molar NaF. Calculate the new pH after the addition of 0.01 molar HCl. Ka of HF is given. The first part of the question is Simple, just a direct application of Henderson Hasselbalch equation. Write down the Henderson Hasselbalch equation, substitute the value of F minus, that is 0.20, substitute the value of HF, that is 0.10, and I get the value of pH as 3.5. Now let's see what happens when I add some HCl into it. HCl will ionize as H positive and Cl minus with the concentrations shown as 0.01, 0.01 and 0.01. And NaF, the present which is already present, will also would have ionized as Na plus and F minus with the concentrations as 0.20 for each one of them. The fluoride ion from HCl will combine, fluoride ion from NaF will combine with the hydrogen ion from HCl, and I get the reaction hydrogen combining fluoride minus HF. So now the initial concentration of hydrogen, fluorine and fluoride and HF are given there. So when the hydrogen ion reacts with the fluoride ion, it gets consumed and concentration of F minus decreases and the concentration of HF increases. So now I have the new concentrations. With the new concentrations for F minus and HF, calculate the pH, and I get that as equal to 3.3. Calculate the pH of the buffer, 0.10 molar ammonia and 0.10 molar ammonium chloride after the addition of 20 milliliter of 0.05 molar HCl to 80 milliliter of the buffer. Kb of ammonia is given. So in this question, first we have to calculate the pH of the buffer, and according to the Henderson equation we need the value of Ka, and hence the Kb, from Kb, Ka is calculated. We know Ka is equal to 10 to the power of negative 14 divided by Kb, and that's what is substituted into the equation. And ammonia will act as the base here, and the ammonium ion will act as the acid. Therefore, since here it doesn't make any difference because the concentration is same, we get log of 0.10 divided by 0.10, and when you calculate the pH, I get it as 9.25. So this is the pH before the addition of HCl. Now, in order to see what happens when I add the HCl, and I'm not adding to the whole of the solution also, I'm taking only 80 milliliter of it. So let me calculate the moles of HCl for 20 milliliter of HCl. That comes as 0.001, and the moles of ammonia and the ammonium ions also comes as 0.008. This is the moles. You can, since the volume is 100 ml and in the ratio it will get cancelled, you can proceed with the moles itself. But here I prefer to convert it into concentration. So I divided it by 100 milliliter or 0.1 liter to get the concentration. And that's what I'm going to use in the calculation when ammonia reacts with hydrogen ions. So when ammonia reacts with the hydrogen ions, I get the ammonium ions, and initial concentration of ammonia is 0.08 and the hydrogen ion concentration is 0.01, that I get it from HCl, and the concentration of ammonium is also 0.08. So the concentration of ammonia, since it reacts with 0.01 hydrogen ion, it will be reduced to 0.07 and hydrogen will become 0 and the ammonium ions will become 0.09. So I have all the values substituted into the Henderson Hasselbalch equation, and I get the pH equal to 9.18.